In this video, we're going to discuss the machine learning and adaptation features of Jube. Jube is free software to detect, prevent, and investigate money laundering, fraud, and compliance breaches. We'll pick up broadly where we left off with a reminder of the abstraction we put in place. So just to remind ourselves, we have created a model so far which accepts transaction payload over an HTTP endpoint, but crucially performs abstractions upon that data using a combination of incrementing TTL counters, abstraction rules, abstraction deviations, and abstraction calculations. So to come to abstraction rules, for the purposes of illustration, you will observe here that we have two rules, velocity rule and velocity rule declined. If we were building out the model, we would endeavor to have hundreds of these abstractions because computationally the data is only fetched from the cache the once, and then all of the processing, all of the filtering that is done with abstraction rules is done in memory. So it doesn't really matter whether you've got 1 or 100. The response time is going to be much the same. And that is the secret sauce to machine learning and adaptation that we'll come on to, creating many abstractions to provide domain experience or domain insight for the machine learning and adaptation techniques, which are broadly commodity, broadly point and shoot. Now, these abstractions doesn't matter if it's a TTL counter incrementation, an abstraction rule value, an abstraction deviation, or an abstraction calculation, or even some numeric values drawn from the payload. All of this can provide immense value to machine learning and adaptation. Data can be stored in a couple of places depending on the configuration. It either ends up in a SQL Server database table, which is just fine for low volume implementations, or it can end up in an Elasticsearch database, which is much the same except is natively indexed, and getting at the data is a little bit easier. In both cases, however, data can be extracted using the Adaptation extraction widget to present data for the purposes of machine learning as follows. On the left hand side, we have the dependent variable, 1 being fraud, 0 being genuine. This means to say that fraud has either been tagged at the transaction level or the case level. Meanwhile, towards the right-hand side, we have many abstractions which have been automatically extracted from the database for us. So the adaptation widget inspects the numeric request XPath or payload, the TTL counters, the abstraction rules, the abstraction calculations, and the abstraction deviations, and passes those out and presents all of this in a tabular format. Whether we go on to perform machine learning in Exhaustive, which is our own machine learning algorithms, or R, this structure is absolutely ideal. As aforementioned, we have an embedded machine learning training algorithm called Exhaustive, which searches for optimal anomaly detection and classification topology. So I'm going to use this data set, which has been created through the adaptation extraction widget, and upload that data set to the Exhaustive training algorithm. So I'm going to click on Exhaustive and I'm going to select Train New Model with the fraud risk dataset, which we have just inspected. I'm going to give this training run a name called video. Description if you so choose, specifying the dependent variable to be of the same name. The next three options allow me to be able to exclude fields, fix fields, or prescribe fields. Excluding means to say the field will not be included in training. Fix means no matter what topology Exhaustive arrives at as optimal, this field will always be in there. And prescribe is slightly different and extremely complex and a little bit outside of the scope of this video, but relates to real-time Monte Carlo simulation. And this is a field that is going to be randomly simulated during recall, with the highest score being produced by the model being the optimal scenario. And for this example, I don't want. So I'm just going to click Start Training. The training job has been scheduled. Now I have to start the training algorithm in the background. The reason for that is that the computation of the Exhaustive training algorithm needs to be separate from any resources dedicated to the processing engine and the user interface. As you might expect, Exhaustive training is computationally very expensive. So I will need to spin up a dedicated server to offload that computationally expensive task. So I've launched the Exhaustive training algorithm. This is a headed Windows client, although it can also run as a console application by just passing it some command line parameters. But it allows me to set various control parameters for the regression and neural network models and the anomaly detection models. So all I've done is transpose the GUID to here. It will load the file, marry up the parameters, but all I need to do is click start because it has already been passed by the end user. The algorithm will proceed to do statistics online, sample the data, work out the best way to go about normalization, and then start some training, which is what you're seeing here. In a couple of moments, you'll see this launch into life in the user interface in the background. And what we can see in both the training algorithm and the background is the performance of the models, and the best model we've come up to at the moment is a score of 83%. So I'm going to leave this running for just 10-15 minutes for a particularly complex problem. More than likely I'll have allocated about 16 cores and I'll leave it running for at least 4 hours. But for illustrative purposes, I'm just going to leave it for 10 minutes and then revisit. Before we look at what has been created by Exhaustive, let's discuss the theory behind machine learning and adaptation. In Exhaustive, there are 2 classification models, regression and neural network, and 1 anomaly detection model, so-called one-class support vector machine. The difference between classification and anomaly detection, supervised and unsupervised learning, is that the classification requires the dependent variable, an indication of whether the training data is fraudulent or genuine, whereas unsupervised learning has no such dependent variable, and it assumes that all of the data is genuine. The difference is a classification will express the likelihood of something being fraud, anomaly detection will express something being unusual. And that correlates well to money laundering and fraud. Here is a visual depiction of a regression model. On the left-hand side, we have abstractions. Each abstraction is being multiplied by a coefficient and added to an intercept to create an output. If that output is greater than 2, it's considered fraud. It's classified fraud. Else it's considered genuine. It's classified genuine. Neural networks are very similar, except the nomenclature changes somewhat. Instead of describing these as coefficients, we describe them as weights. Instead of describing this as the intercept, we'll describe it as the bias. We also describe the summing up and the threshold. In the previous example, if it was greater than 2, it was considered and classified as fraud. We describe that as an activation function with a simple yes or no, 1 or 0, an output being signaled forward. Notice the language I use, signaled, representing the flow of abstraction through this model. The activation function in the previous example, it was just a threshold saying if it's greater than 2, then it is considered or classified as fraud. If it's less than 2, it's considered or classified as genuine. A threshold is the simplest to understand, but the signal forward doesn't have to be just a 1 or a 0, a yes or a no, that binary outcome. It can be transposed using a function, in this case a sigmoid. The problem is, it's very difficult to know which activation function to use. There's quite a few of them. The neural network I presented first was a little bit simplistic. Neural networks have so-called hidden layers, and inside these hidden layers are processing elements. The idea of these hidden layers and processing elements is that they are effectively models within models. They handle abstraction that intuitively we might not be able to arrive at ourselves by just creating abstraction rules. The difficulty is it's quite difficult to know how many hidden layers there should be and how many processing elements there should be in each hidden layer. And that, in conjunction with the activation function, upon a random selection of abstractions randomized at the start of each hidden layer and processing element exploration, is what Exhaustive is exploring. It will try a model with 1 hidden layer, 1 processing element, add another processing element, then another, then another, then another. When it reaches a certain width, it will spill over into another hidden layer, trying 1 processing element in that hidden layer, then another, then another, then another. And for each layer, it's trying different activation functions, and it will create hundreds, if not thousands of models, making predictions, testing it against what actually happened, seeking improvement through classification accuracy. The problem with classification systems in general is that things move on. What happened yesterday is not necessarily what is going to happen tomorrow. So by their nature, they're very biased towards problems that have long since passed. So that leaves us with a problem in identifying new typology. For this reason, we use one-class support vector machines to detect an anomaly, which is not presenting likelihood of fraud or money laundering, but rather saying this is extremely unusual. And in this example, not a great deal different to a clustering model. Over here we have in the blue something that's a bit unusual we might want to have a look at. Over here we have something that is quite normal, really contrasting the volume. So it looks a lot like clustering, except it has a slightly different technique, because this line going through the middle separating the anomalous cluster from the seemingly normal cluster is called a support vector. It's a lot more complex than that, but Jube will automatically create a one-class support vector machine across all of the variables presented to the model, such that it's able to identify when the environment starts to become more strange. What happened yesterday is not necessarily what will happen tomorrow, and classification is biased towards that. So let's roll forward 10-15 minutes, and the training job has been stopped. It promoted 8 neural networks, and since it promoted the best neural network, there has been 15. Had we let this run, it would have stopped at the point it got to 100. Let's have a look at the best model that has been created by the system. So in the top left, we have an errors histogram, and what I'm looking for is for it to be reasonably tight around the mean and ideally normally distributed. The model is going to make errors. What was predicted is not always going to be what actually happened, but we're looking for the score of 83, which is a mean of the Spearman correlation, the mean, and the percentage correct. We'd be hoping it gets it right 80% of the time. So the errors are relatively small, all centered around the mean, and these longish tails, so that's okay. The predicted versus actual chart is a little bit less intuitive for classification problems. It's better for numeric prediction. But the confusion matrix is vitally important for assessing the classification accuracy of a model. Up in the top left-hand corner of the confusion matrix, we predicted positive. It was positive 226 times, which means to say we're getting it right in the order of 85%. So that would be a true positive. We predicted it was not fraud, and it was not fraud 242 times. True negative. Let's have a look at the sensitivity now. We predicted it was fraud, and it wasn't fraud 31 times. That's your archetypical false positive, oftentimes focused on by the business, but not necessarily the best statistic to focus on. Meanwhile, we predicted it was not fraud, and it was fraud 41 times, false negative. In a high impact, low probability problem like anti-money laundering, I would suggest that false negatives are a big issue. So the two values in the confusion matrix that you might want to dwell on is your true positive and your false negative. Over here, we have the receiver optimization curve. And what this shows me is a trade-off between the false positive rate and the true positive rate. It's a visual representation of how sensitive my model is. And what I want to be seeing is that curve pushing right the way up into the top corner. A completely diagonal curve would mean the model is junk. A completely right-angled curve would mean the model is flawless. But in practice, what you want to see is that curve getting up as far into that corner as possible. So all the indications of the summary statistics of my model is quite reasonable, the highlight being this score. Scrolling down, we can have a look at the training experience. This is described as a learning curve, yet the reason it's not going upwards only is because we allow the model to flutter between about 5% on the score. The reason for that is neural networks in particular are quite prone to overfitting. So as long as it is within 5%, we would like to capture that model and give the end user the option to use it to do various experimentation. The score won't be classed as the best score, but the model is still available. Again, especially with neural networks, a model that is slightly less accurate might actually perform better in production. So the reason we allow that flutter is to give some choice to the end user, as we'll come on to in a moment. The first stage of training was statistics, summary statistics and analysis on all of the variables passed in the dataset. What it also does is it looks for the relationship between that variable and other variables, so-called collinearity. And in this case, what I can see is that foreign has a correlation of 0.68, so it's quite a strong relationship to the dependent variable. And it also has a very tight relationship to whether the customer has been abroad or to a high-risk country, which is logical. It also has a reasonably strong relationship to count unsafe terminals. And the reason we might like to see that is because it gives us a sense of whether this variable is telling us exactly the same as another variable, and we can pick the one that makes the most intuitive sense. As we saw from the learning curve, the fluttered learning curve, many models have been created, and given enough training time, it's always going to be a neural network that wins out. If I wanted to toggle this one off, I would just click that button. Let's look at the model that has been created in this instance. So Exhaustive has determined that these are the most relevant independent variables, ranked in order of their importance, the most sensitive to the least sensitive. We're able to test by performing simulations. So let's suppose that the different decline reasons seasons in a day is 2. This influences the score in real time. What is actually happening here is that this tool is making an API call to the engine. So the exhaustive model that we've created can actually be called directly by HTTP. And as we'll come on to in a moment, it is most powerful when it's embedded into the model. So I'm changing these sliders around to test my model. The ranges specified here are the minimums and maximums that were observed in statistics. And what we can see is we've got a score of 0.95, which means that it's very likely fraud, and it's also extremely strange. The anomaly detection score is very sensitive. So because I'm randomly selecting these values, it is very strange. But we'll do a batch test in the moment against real data to see how the anomaly detection score performs. It would be quite painstaking to take the contents of my Excel file and put each record through this simulator. So we can do a batch test. I'm going to select the same file I used for training. Now, although Exhaustive will divide this file randomly into training, cross-validation, and testing datasets, so the score can be trusted, it is advisable to never test on the same data you used for training, which is what I'm doing in this example. So a little bit of license. I'm not doing any Monte Carlo simulations. If you recall, we had the ability to be able to set variables to prescribe, but we didn't do that. So it's a straight through recall of the model. So I've put the GUID in the same manner as I will in adaptations in just a moment, and I'm going to click recall and simulate. The progress will be written out as below. So on completion, several outputs. Notice an Excel file has been created and downloaded. Up at the top, I have the score histogram. This is showing me the distribution of the scores. Now, ordinarily, if this was done on a completely random population, keeping in mind that this data set is oversampled, so 50% fraud, 50% bad, which is not what you'd experience in production. We'd expect something a little bit more logarithm, but it's showing me what scores have been achieved for each transaction. The histogram below is a similar concept, yet it is based upon the anomaly, and that has a similar issue that we just described in that this dataset is oversampled, so ordinarily we would expect that to be slightly more logarithm. Let's open up the recalled model. Just as a reminder, I've got my dependent variable on the left hand side. This is what actually happened. Now, over the right hand side, I have the score ranging between 0 and 1. The higher the score, the more likely it is to be fraud. Let's have a look to see if the prediction was accurate. So if the activation, meaning to say that it's over 0.5, the score, is equal to the dependent variable, what actually happened, then it's correct or it's not. And let's fill that down. So let's just do a very quick sum of that column. And it shows that I've got 1, 5, 3, 6, which are correct. So by taking the smaller value, dividing it by the bigger value, we get an 84% correct. Pretty darn good. Another statistic I might be interested in knowing is the relationship between determining fraud, keeping in mind it's correct 84% of the time, that determination of fraud, and anomaly, because they're totally different models, and we're pinning our hopes on anomaly for this model to detect new fraud and money laundering typology. So I'll just do a quick rudimentary correlation between the score and the anomaly. I have a relationship of 0.59. That is a very strong relationship between the score and the anomaly, which means to say as the score goes up, so too does the anomalous environment. This is great. This means to say that we can trust our anomaly score identify new fraud and anti-money laundering typology. The ultimate outcome for us, however, is to integrate this model into the real-time processing, keeping in mind that we've created abstractions, abstraction deviations, abstraction calculations, TTL counters, all of which can be matched into the exhaustive model that we've created. So to wire it in real time, that would be an adaptation. So to create an adaptation, let's call it exhaustive. and select the Exhaustive radio button, which accepts my exhaustive GUID to be executed. Before I click Add, our Plumber is an outbound HTTP POST to an rplumber instance. What that is intended to allow is the invocation of any models that might have been written in R. They're not going to provide the real-time performance, and it comes at an interoperability cost. So I'm going to use Exhaustive. I add that model, and I'm going to synchronize. And over to the simulator to send in a post, and it can be observed that in the same manner as the simulator in the Exhaustive training page and in the batch recall, Exhaustive has been recalled, creating a score of 0.21, an anomaly of scientific notation, something very small. Noting that the fields that we trained the model with are not actually available in either the data payload or the abstractions, abstraction deviations, calculations, or TTL counters. In such an instance, the value will be swapped in with the average observed from statistics established during training. It naturally follows that the adaptation can be used in rules, whereby I can use either the score or the anomaly detection to set thresholds to activate. Jube is free software to detect, prevent, and investigate money laundering, fraud, and compliance breaches. It's available at Amazon Web Services Marketplace.